Declan, forgive me, I'm going to mostly read about this so it gets out there. So Declan, Mages. By the way, what type of name is Mages?
Irish.
Irish. Okay.
Oh, Declan. Oh,
okay. Bohemian. You mean like?
Off to a good start.
Okay. He doesn't even know where he's from. And Declan, if you don't know where you are, you can't tell where you're going. Okay. Just a little navigational trick there. Okay. Oh, we're off to a great start, aren't we? Okay. You do better at JPL, I hope. Declan is a navigation engineer at the Jet Propulsion Laboratory's Outer Planet Navigation Group, specializing in optical navigation. He's an East Bay native, having grown up in Oakland and graduated from Chabot Elementary. Where is Chabot Elementary?
Rockridge.
That's right. I've actually done a program up there as the Astro Wizard. And then he went to Claremont Middle School and Oakland Tech High School, which I also attended very briefly for a summer program, but that has nothing to do with this program. He went on to earn a master's in aerospace engineering from Cal Poly San Luis Obispo and got his start at JPL as an intern working on optical navigation for the New Horizons flyby of the Kuiper Belt object Akaroth, boy, that sounds ominous, where he researched and implemented dim target registration techniques. And we're really big fans of New Horizons here because Dr. Jeff Moore is one of our big friends here. Okay, let's see. And okay. Starting full-time in 2020, he worked with JAXA, the Japanese Space Agency, to navigate Hayabusa 2 on its sample return trajectory, which is a very successful mission, and on optical navigation for the DART and Lycia Cube missions to Dimorphos. And of course, if you remember DART, that was where they successfully collided an impactor with the, I think it was with Dimorphos itself to change its trajectory slightly.
Yeah.
Okay, good, I got that right. And current mission work includes optical navigation for JAXA's Martian moons exploration mission to return samples from Phobos, which is really exciting, I think, and Mars sample return. Good luck on that one, given funding. Oh, his recent research interests have included rapid response missions to interstellar objects. Whoa, that sounds impressive. Uranus, aero capture concept development. I didn't know they were working on that. And autonomous optical navigation, which, if you think about it, could put you out of a job. So I wouldn't recommend pushing that too hard. Okay. Anyway, so without any further ado, Declan Mages from JPL.
Okay, coming through. Okay. Yes, thanks for the intro. Very happy to be here. I'll be covering deep space optical navigation. Hope you guys will all find it very interesting because there really is a lot of overlap with astronomy. Official title, navigation engineer. Little bit of a regurgitation here. I can kind of skip over. Started in 2020, January 2020, officially full-time in the Outer Planet Navigation Group in JPL's Mission Design and Navigation section. Little bit more about at JPL. Again, Hayabusa 2 is really the first mission I got to work on. At the same time, jumped right into working on DART and Lycia Cube, and DART is a APL, Applied Physics Laboratory mission, and Lycia Cube was run by the Italian Space Agency. Was always, my master's thesis was on rapid response concept analysis to interstellar objects. If you guys were, aware of Oumuamua and 2I Borisov, those are kind of fresh off the press when I was doing my master's thesis, and so I was looking into concepts to try and intercept those. I've been working on Mars sample return, doing some work investigating Enceladus missions, working on a lot of autonomous navigation, Uranus aero capture, exploring that as an option to enable kind of, the next flagship mission after Mars sample return has been highlighted as likely a Uranus mission. So there's some early work looking at that and how we can do that in a timely manner. Otherwise, working with JAXA again on the Martian moons exploration mission, MMX. And then doing some more planetary defense type of work, looking at a little bit these days at some ion beam asteroid deflection. So quite a grab bag. It's kind of a great thing about navigation. You kind of get to get your feet into everything. So about deep space navigation. So very high level, the highest level of what does it mean to do deep space navigation? It's kind of broken up in these 5 steps. We have the tasks and then an example on Earth and then what that really is in space. So step number 1, if you're going to do navigation, is you need to obtain a map. So on Earth, you need to know what your roadmap is, have an understanding of the terrain around you, And in space, that really is knowing where everything is, knowing the ephemerides of all the major bodies, of everything that's going to be, expressing a gravitational force on your spacecraft, understanding all the things that are going to happen to you on your journey, and how you can plot your course through that. And that really is developing these ephemerides, and that's a key role that's done at JPL, and especially during early navigation was there was a lot of dedicated effort to really figuring out where the planets really are. And then of course you have to develop a travel plan. You know where you want to go. And on Earth, that's selecting your trail to get to your destination, planning things out time-wise. When are you going to get there? And in space, that's designing your trajectory. You come up with your trajectory to reach your target. Do you want to do a flyby, get into orbit? Where do you want to go? What are the, gravity assists, all of that. You have to create this trajectory, this plan, your nominal trajectory. And then when you're on that journey, once you're have this travel plan and are now going out to get to your destination, you have to keep track of where you are the whole time. You have to, in order to get there, you need to take meaningful measurements. You need to, when you're on Earth, you're looking at your map and saying, oh, okay, it looks like on based on where this figure in the distance, this mountain range, and I can see the elevation. Okay, I should be right around here. It looks good. I'm on course. In space, that's really collecting radio signals or optical measurements to estimate where you are on your trajectory and understand if you're still on that right path. And with these measurements, you're bringing that all together really into step 4, which is to calculate one's position. You have all these measurements, and now you can look and say, where am I with relation to my travel plan? And then the final step is you look at all of that, and you have your plan, but then you have where you actually are. You need to develop a new plan, a new optimal plan. You're never going to nail things exactly perfectly. You're never going to be exactly on the trail. So what do you then have to do to get back on track, to get to your, to get to that flyby at the exact right time in the exact right position? Or on Earth, we're not going to make the bus. We need to speed up a little bit to get there on time. And that's kind of the very high level, just what it fundamentally really is to be within the mission design and navigation section and to do deep space navigation. It's all about developing this plan, having your orbit, and then tracking, making sure you're on that plan, and then figuring out how to stay on it, and characterizing anything that is causing you to deviate off of it. So how is that done for near Earth, when we're near the Earth? Very conveniently, we have the Global Positioning System, GPS, which all of us rely on every single day and is enormously useful for spacecraft as well. Basically, there's this constellation of satellites, the GPS satellites. They transmit time tag signals with information on their position, and then all of the devices that we have that have GPS receivers get those measurements, and they get measurements from multiple GPS satellites, and you have the knowledge of where the satellites are and the time that they sent the transmission, and your phone or your device can look at when it was received. And you basically have all these range measurements from all these satellites. And with that, your device can determine where it is, basically. And so it's just constantly transmitting this information that allows you to just, near perfectly, to meter level accuracy, pinpoint exactly where you are at some exact time. And it's just extremely useful. However, when we're in deep space and doing interplanetary navigation, there is no GPS. The signals just aren't strong enough. There's some work looking into using faint GPS signals around the moon, but that's really kind of pushing the ultimate limit of where you could get your leverage GPS data. So instead, we have the Deep Space Network, or DSN, commonly referred to. And so as you can see kind of in some of the graphics, it's primarily 3 stations. This is established in 1958. Originally, the DSIF became the DSN in 1963. But so there's these 3 stations in Goldstone, California, Madrid, Spain, and Canberra, Australia. These are stations managed by the Jet Propulsion Laboratory. And they're basically collections of just enormous dishes. Most of them are 20 meters, 30 meters. Several have the largest dishes, which are 70-meter diameter dishes. These huge communications arrays that have been positioned. You can see the top-down view. They've been positioned basically in, cut up three and divided evenly across the globe 3 ways to give complete coverage of the solar system. Of course, there are these little gaps, but that's where you can get, your GPS data in between these gaps. But the point is basically that any spacecraft in interplanetary space that's meaningfully far away from the Earth will always be able to see at least one station at all times. And that's really the point of these. I think there are technically some blind spots directly above and below, but spacecraft essentially never ever go there, so that's never been an issue. I'm sure it has, but generally in interplanetary space, you're just way out away along the ecliptic, along the orbit of all the major bodies and asteroids, and so you at any point in time will always be able to communicate, which is a key thing. You're flying these multi-million-dollar missions, billion-dollar in some cases, and so you need to always be able to communicate when you need to, and that flexibility is key to being able to operate out there. So what are these measurements that we're collecting? So there's three main data types that the DSN uses to track our spacecraft. That is Doppler data, range data, and delta differential one-way range, or delta DOR. So the real bread and butter of navigation is Doppler data. And at a very, very low level, Doppler data is a measurement of the Doppler shift, which is, if people aren't familiar with that, that's the phenomenon of, if you can picture a car honking at you as it drives towards you, and you hear the change in the frequency of that honk, or if someone's yelling at you and they run right by you, you hear a ring, that change in frequency and change in sound is due to the sound waves being compressed and stretched as the sound comes towards you and then comes away. And so your ears are hearing different frequencies due to the motion of the object that is transmitting. And so we basically take that and you do that with radio waves. You basically communicate with the DSN in various bands, and you measure the change in that frequency over time, often over 8-hour passes, multi-hour passes. You just get a clean measurement of the change in the line of sight range. It's your line of sight range rate. You don't know how fast you're moving side to side. You just only know how fast the spacecraft is moving away from you or towards you. And it creates, basically, over time, you get this signature in the top right. You basically have this over exactly 24 hours, this cyclical sinusoidal signature due to the Earth. The Earth is spinning around. So if you think about a spacecraft being completely still and you have your station on the Earth, as the Earth spins, you're going to be moving towards the spacecraft and away from it because you're spinning around the Earth. So you get this cyclical signature due to the Earth's motion, the Earth's spin, and then you have these, imposed on top of that, you have a long-term trend, and that's the spacecraft's trajectory as it's more gradually moving away from you or towards you in the solar system. And so those two are kind of superimposed on each other, and you get a lot of kind of insight into the shape of that sinusoid and the shape of that larger trend, and allows you to estimate velocity components of your spacecraft trajectory. And that's, again, GPS gives you these perfect little single position measurements, and the Doppler data gives you this velocity measurement. And that's really the fundamental bread and butter of deep space nav is getting these measurements and putting them together and creating a trajectory. Otherwise, there is also just range data. You send a time tag signal again. You say, here's the signal at this time. When did you receive it? When does it get sent back to the DSN? What's this round trip time? You can kind of get a range measurement. And then the final measurement is this kind of more complex measurement, delta differential one-way range. It's basically a fairly novel, more complex measurement that's extremely powerful, where you have two stations sync up and measure signals from a nearby quasar, and then immediately go collect signals from the spacecraft. And you know the signal of the quasar and where exactly the quasar is. And the quasar is you guys can probably explain things better than me, but a distant black hole that is creating a massive jet of energy as its excretion disk around it is just sending out massive amounts of energy. And so we know where these things are, and we know where they are very precisely. And so we can collect signals from them and get this really clean measurement, and then measure the spacecraft and eliminate a lot of noise sources. So it's this very powerful measurement that allows you to eliminate noise sources from the atmosphere and get really precise angular measurements of your spacecraft. And that's just, one of the more complex. It's been implemented most recently and is very powerful. And otherwise, a lot of these, there's a lot of error sources. It's all about modeling all of these things. And the key error sources, a lot of this is, I'm talking about a lot of things that are related to timing. Timing is your most critical error source when doing navigation. If you're, things are moving at such great speeds that if you're off by 1 second, you're off by hundreds of kilometers. But we really care about, you'd start talking about nanoseconds in some instances for some of these measurements. And then, you're measuring where all the stations are, because the stations are collecting all this data. We need to know exactly where they are in order to connect things. The Earth orientation. What is the exact orientation of the Earth in order to remove this cyclical pattern? You don't want to have your Earth spin mismodeled and take some of that spin signature and put it in your spacecraft and completely throw off your estimation. So all these things, it's taking all these things and doing them as precisely as possible. And then we have kind of what I mainly focus on is the optical navigation side of things. So basically with all this DSN data, we're talking about measuring where the spacecraft is. But we're going out to these bodies in the solar system. We're going out to asteroids. We're going out to distant planets. We're going out to all these locations. And we can know where our spacecraft is extremely well. But how do we know exactly where our destination is? And so this is where optical navigation comes in. It's basically, we often know where the asteroids are and these outer planets till hundreds of kilometers, which just isn't really precise enough to do the meaningful science and get into the precise trajectories and orbits around these bodies that we need to. And so we put a camera on the spacecraft, and the spacecraft on approach to these targets can take pictures. So you can take a picture of this asteroid as you're on approach and refine its trajectory using the spacecraft itself as it heads there. You basically get this really powerful measurement because a lot of asteroid ephemeruses or trajectories have been estimated and defined by assets around Earth. We have telescopes around Earth or in orbit around Earth. And so they're kind of limited by these great distances where these asteroids are really far away. So even though they're extremely powerful telescopes, there's still this fundamental limit of these massive distances. Well, whereas the spacecraft is inherently going there. So it's completely collapsing this distance down to, these really short ranges where even though the camera on board the spacecraft is not as good as Hubble, but it's 1,000 times closer than Hubble. And so you really start to get these incredibly powerful measurements up until, you're right on the thing and then you know exactly where it is. And so this is kind of where I really got my start and where I've been working most of my time at JPL is on this OpNav. I think, to go into that a little bit more. So again, very powerful measurement because of these short distances. What are the steps? So again, it's developing a plan. You have your trajectory, and we need to look at when we can take pictures. What are the constraints? Then, of course, the spacecraft get launched, and now we're on this trajectory. First step is calibrating the cameras. Everyone always always have to calibrate the cameras. We care about measuring everything as precisely as possible. So there's a camera calibration step. I'll kind of walk through that in more detail later on. And then we have to collect our measurements, in which there are two main categories: unresolved targets, point source targets, and fully resolved targets. That's kind of the two distinct types of optical navigation and ways that things are approached. And I'll go through several missions with examples of both later on. And then just to kind of touch on this last step, there's all these measurements we're collecting, and then they have to get brought in, and then we do orbit determination. So JPL kind of has this flagship software called Monty, in which we are able to model the universe and model all these measurements and bring them all together to estimate the trajectory, estimate a bunch of different things. We're estimating maneuvers, we're estimating the solar radiation pressure, errors, we estimate pole, you estimate gravity fields. Gravity science is really tied hand in hand with navigation because you're estimating, a colleague of mine just published a paper estimating the moon's harmonics down to the 1,800th order by just modeling all these things so precisely. You estimate, you need to understand everything that's going on, all the forces and dynamics. There are things that you'd consider that you want to take into account uncertainties, but don't necessarily estimate, like a lot of these parameters, atmospheric effects, station locations, Earth orientation. You try and model everything, even if you don't want to estimate it. You want to understand how our uncertainty of it is affecting everything. It's not just about knowing your trajectory. It's about knowing how well you know your trajectory. I know I have an estimate that I'm here. How accurate do I think that is? And you need to fold in all as much as you can to get that and get that accurately. And then we track all these small forces. Is there a little bit of outgassing going on the spacecraft that we have to take into account? And basically all that gets put together into the most simple description is a least squares fit. If you've ever thrown up data points on Excel and said fit a line to it, it's at the very simplest level what we're doing. We have all these data points, and then our line has all these axes and all these parameters, and we're basically fitting all of those data points and fitting a line to that data, and that's our trajectory basically. And that's kind of completes and with that we have our trajectory. You hand that over to the science team to plan the acquisition of measurements, to design maneuvers, and to fly the mission. A little bit of a slide on kind of some metrics for navigation performance. This is, I think, just an interesting thing of like how do we talk about how well we're doing basically. There's a most common formulation that maybe you'll see in discussion about navigation is the B-plane. Basically, in this graphic here, we have an asteroid and we have a spacecraft that's passing by it. You basically take the velocity vector and you create a plane perpendicular to that, and then you really try and model where you are going to cross in that plane. And a lot of requirements are defined in this way of like, we need to pass by this position within this ellipse and within a certain time range. So you really are looking at like where you're crossing in that plane and at what time you are, the time of flight. And so this is kind of how requirements get defined. You're allowed to, you say you have to, we have to hit this ellipse, this circle within 15 kilometers. Okay, so we have to get our trajectory there, but we also have to get our uncertainty of the trajectory to fit within a certain region in order to do a gravity assist, to fly by an object and collect the measurements in the way that we want to. And there's different ways that it's formulated for when you're in orbit around a body, because the B-plane formulation doesn't really apply when you're orbiting something. But yeah, so that's really kind of what we're tracking. We're tracking some other orbital parameters, and then we're always tracking the delta V. That's kind of the big key thing is, if we're doing really bad navigation, then we're going to be bouncing around all over with these, as our estimates shift around. If we don't model things correctly, you shift around and you're constantly correcting for your own errors. And so you really are trying to keep track of the delta V and minimizing the delta V. If you minimize the delta V, the mission can go on longer, or you could do an extended mission. And the mission can execute even at all. Now, going to do a big blurb on the history of deep space navigation. A lot of this before my time. Origins kind of really do essentially all originate at JPL. Starting with the early Mariner missions. This is 62 to 67. I'm going to try and just hit, I started filling this out and started just listing out every interplanetary mission and had to figure out a way to trim it down. So trying to focus purely on relevant navigation events and missions that had relevant milestones, because otherwise it would be here for an hour. But yeah, early Mariner missions really, they were sent to do flybys of Mars and Venus really initially limited navigation. This is when I think the DSN wasn't still officially called the DSN. These missions really had some tracking data, but they would only basically perform a single burn. Soon after launch, you kind of clean up your launch error, and then you just fly out there and see where you end up, basically. So they would target distant flybys because you had these large uncertainties of where exactly you'd pass by. So you'd basically just do one burn and just see where you flew by. Relied on just purely Doppler data. Mariner 6 and 7 were the first demonstration of optical navigation. Then in the late 60s, range measurements were added. Mariner 9 relevant is the first orbiter mission. A metric here we're able to predict the spacecraft's location 9 orbits out to within 4 kilometers. So doing pretty well already at this point in time, in 71. These are all their launch dates. And then 73, Mariner 10, that was the first gravity assist. They were performing, at this point in time, multiple maneuvers on the trajectory. TCMs, I think I skipped over, stands for trajectory correction maneuver. A maneuver to bring yourself back onto that planned trajectory. And then, yeah, performed a flyby within 17 kilometers, doing fairly well at that point. Pioneer 10 and 11, they're the first missions to the outer solar system, performing flybys of Jupiter and Saturn. So again, we're starting to get to these greater distances now, getting to fly out there. And then iconically, launched in 77, Voyager 1 and 2, really pushed a lot of boundaries with navigation. We went into new frequencies to get more improved measurements. The first missions that required optical navigation. Past times it had been demonstrated, but it was not needed to meet navigation goals. In this instance, again, we're going out so much farther. The outer planets are so much farther away. We didn't know their orbits very well, and we had interest in collecting measurements of the moons. And so this is where you really had to send your spacecraft out there, collect those measurements when you were close by in order to execute the science goals. And so this was the first required use of optical navigation. And also, yeah, we're going so far away. This is when the DSN gets its 70-meter dishes. Gets the larger the dish, the more signal strength you're able to transmit with, and the more signal you're able to collect to have enough signal to noise to have these communications at such great distances. 84 to 85, Halley's Armada, really incredible series of missions that I think don't get acknowledged enough. So this was a series of 5 missions. NASA actually didn't send one out to do flybys of Halley's Comet. Each one basically was sequentially improving the knowledge of the orbit so that the following ones could pursue closer and closer flybys. And to date, it's the fastest flyby ever performed at 68 kilometers per second, which is truly incredibly fast. I think a comparison I'll talk about later with the DART was 8 kilometers per second. So that's we're almost talking about 10 times the speed. It's truly incredible how fast these flyby were, because Halley's Comet is just careening through the solar system at such high speeds. Really incredible mission there. Then Magellan to Venus was the first use of air braking, which was a significant navigation challenge. Usually we have full control over exactly how our thrusters are going to fire and what's going to happen. Now you're doing maneuvers using the atmosphere, and so it introduced a new challenge on how do we, correct that, plan for that, predict what's going to happen accurately, so that we can, pump down our trajectory, and how do we make sure we're measuring what happened correctly, and all of that. So interesting there. And then Galileo, first mission to fly by an asteroid and orbit an outer planet. This is another iconic JPL mission that had its high gain antenna. It failed to deploy, so the mission was flown using only a low gain antenna. There was lots of innovation with OpNav because of this limited data rate. They had to really pursue ways to compress the OpNav data as much as possible, and it was really key for the navigation goals in order to get enough data down. And so a lot of novel approaches. Noted. First use of CCDs at this point for optical navigation. Near Shoemaker, first mission to orbit and land on an asteroid. And at this point in time, we're talking about rendezvousing around asteroids. And to get into orbit around one, you're no longer flying by it. You're now around it. So how do you navigate around this, rocky body? And at this point in time, they used crater landmark-based optical navigation. So you're looking at craters and registering them and tracking them as you move around, to get an estimate of how you are moving around this body. Cassini, just have to put Cassini. 1990, launched in 97, and really considered a Rolls-Royce spacecraft of just extremely precise navigation. I mean it was just you could fly this thing with extreme precision. Every pretty unprecedented amounts of effort gone into modeling every single aspect of that spacecraft so that you could fly it with as much precision as possible. 98, relevant mission, Deep Space One. This was really a big technology demonstration mission, and this was the first demonstration of using ion engines, and also autonomous optical navigation during cruise, and autonomous optical navigation during flyby of a comet and asteroid. So I'll touch on that more in detail, but that was launched in 1998. Then also in 98, Mars Climate Orbiter. This is, I remember learning about this in high school. The very famous navigation mishap, where basically the thrust force files that were being ingested by the navigation team were expected to be in Newton seconds, but were in pound seconds, resulting in a large error, over a factor of 4 difference in the forces. And this issue was just essentially not properly diagnosed, and ultimately led to Mars Climate Orbiter passing by Mars at an altitude of 57 kilometers, which is an unsurvivable range where the atmospheric forces destroyed the spacecraft. And so this was kind of a really, huge event in the navigation community, especially at JPL, led to a lot of new practices being established, the establishment of the Navigation Advisory Group. I've gone through a lot of these. If you're ever flying a mission coming up on a critical event, all the ACEs, all the top navigators will form a review board, and you have to explain what you're doing for every critical event. And they really is this intense review system that's now been built into navigation. It also led to the widespread use of that measurement, delta Dor. That measurement wasn't getting used quite as much, but if delta Dor had been used more for this mission, its power would have exposed this error. Essentially, it's there's a lot of things that was tough with this error. This was going on, but like I said, Doppler data measures only along the line of sight. You can't see any side to side. So all the thrusting that was happening side to side, you couldn't directly observe with your Doppler data. And so it could kind of hide. And so that's where you have these alternative measurements that can expose issues that relying purely on Doppler data might not otherwise reveal to you. 1999, Stardust mission, flew by multiple comets, autonomous navigation for flyby tracking. Flyby of Anne Frank was fully autonomous detection, and the mission wasn't detected by the ground and was detected autonomously by the spacecraft. So that was, I think, a powerful thing. I'll talk a little bit more about those later as well. JAXA Hayabusa mission, first sample to collect asteroids and return to Earth, enabled by optical navigation. Deep Impact, launched in 2005, further pushed autonomous optical navigation, using it to guide an impactor to impact Temple 1. So that was a pretty impressive mission. There's some pictures there. Then, of course, New Horizons to fly by Pluto, and then Kuiper Belt Object Arrokoth, most distant flyby ever. 12-hour round trip light time, really some pretty crazy experiences navigating and then not getting to hear back for 12 hours as to what exactly happened. Dawn mission also pushed ion propulsion, led to new navigation technologies getting developed. Marco spacecraft, first interplanetary spacecrafts, CubeSats. CubeSats, they're very cheap, and they can be cheap missions and cheap to build, but unfortunately for the navigator, they are therefore the hardest to fly. And so that's an interesting dynamic there. As spacecraft go cheaper, they do get harder to fly, and so there is a trade-off there, which is interesting. And then DART, I have to highlight DART. That was most recent use of terminal autonomous optical navigation, managed by APL, their smart nav system, and that was the mission that I got to work on. So, not quick history, not so quick, but there we go. Now onto optical navigation. So I'm going to go through all of this basically in the context of the DART mission, which is where I got most of my experience most recently in a flight project. So DART was launched November 24th, 2021, with the goal of impacting Dimorphos, the small moon of the Didymos system, on September 26, 2022, kind of a graphic of the DART spacecraft. Again, this is an APL mission with nav done by JPL. JPL often works with other centers to do nav. And yeah, there's also the LishaCube CubeSat that I was working on, the OSSI, Italian Space Agency. They collaborated. And yeah, the goal is to impact this 160-meter object and change its orbit. With the real driving science goal is understanding momentum transfer. This graphic kind of represents that. If you impact an asteroid and there's no material shoots out, you don't get that much momentum exchange. If you impact an asteroid and you get a little bit of ejecta, you can, you basically, the ejecta shooting out the back is almost like a thruster firing. It's firing material out the back, and you get more momentum exchanged. It's really important to categorize and understand what kind of additional momentum exchange you can get from an impactor mission, because that, it can be multiple factors. It can be, a 3x factor on your momentum exchange. And that if this asteroid's coming to Earth and we know we need 3 times less spacecraft to deflect it, that's a big deal. So it is important for a kinetic impactor concept to understand this this characteristic of ejecta. But yeah, so getting into the OpNav side of things a little bit, we have the imagers, the Draco camera based on the New Horizons LORRI imager. We had a 9.45 microradian angular pixel size. So in optical nav, we typically describe things in microradians. I believe you guys know an arc second is like 6 microradians, or if anyone knows. Yeah, that's that. I know. Yeah, 2 pi is 180, so we can do that. But yeah, so it's a very, very precise imager. The LORRI camera it stands for long range reconnaissance imagers, LORRI. So Draco is just very accurate, narrow angle camera. The field of view is 0.3 degrees. If that gives some context for some scopes. The total field of view of Draco and LORRI is 3 degrees, or 0.3 degrees. Sorry. Yeah, various parameters. We are limited in our exposure time, so kind of here's a little bit of our schedule, and here's a plot of Didymos's apparent magnitude over time. So starting up above 15th mag, which is when we got our first detection, 60 days from impact, up to when our official OpNav campaign started, 30 days out from impact. And here's kind of our general plan. We were taking 240 images every 5 hours. We were really taking a lot of images. It's not standard. It's because we were pretty close to the Earth the whole time, and there weren't other science instruments collecting data. It was, the spacecraft was built to hit the asteroid with this camera, and so there was no real competition with other instruments in terms of downlinking data. So we just took a lot of images. The last OpNav was taken at 48 hours out from impact. The I minus is impact minus. So impact minus 48 hours was our last measurement used. So 2 days to design our final maneuver. And our final maneuver was executed 1 day before impact using the ground. And then after that, our final ground data point was collected 12 hours from impact to do a final knowledge update, to just tell the spacecraft at 9 hours out saying, we think you're going to hit the spacecraft here. And so this was kind of just our high level navigation schedule. So of course, during cruise, I kind of mentioned that you have to calibrate the camera. They're very well calibrated on the ground. However, you go through launch, there's thermal effects, jitter, all these crazy forces that can mess things up. So it's always important to recalibrate in a space, and once you're in that space environment. So for this, we imaged the Great Pegasus Cluster M15. Here's kind of just a nice graph of how you kind of slew your field of view around and get great coverage to really get a full sampling of the pixel line space in your image, and then you can register all the stars, and then with all these known points, estimate the distortion parameters in your system. And yeah, you calibrate your optical and geometric distortions. You also are able to measure your alignments. A lot of things get unaligned. Otherwise the spacecraft knows where it's oriented based on a star tracker and IMUs and inertial measurement sensors, but the alignment between that star tracker and your camera gets changed during launch. And so it's really important to know that when the star tracker is telling the spacecraft you're oriented like this, what does that mean for where the camera is? And so you want to apply corrections to that alignment. And then yeah, and have to do all this, and kind of here's a graph of the distortions we modeled. So up to around 0.3 pixels, pretty typical for distortions you would expect, and that is to the level we do care about. Yeah, getting into some examples of the images. So of course, step one. So we get our data, our image. We get an estimate from the star tracker and from the spacecraft system as to where it thinks the picture is pointed, and we use that data to load in a star catalog. This is essentially plate solving, where we just predict where the stars are in the background, look at where the stars are in the actual image, and register them. And we have an automated process to do this, do various center finding techniques, compare a lot of the results, check the precision of these measurements over time. But yeah, the basic goal here is to form this registration. And then we have, we collect tons of images. If you can see here, there's, we have all these stars, but where's Didymos? We don't have our target. And so what we do is we collect many, many images, and then we co-add them. Various methods. The drizzle technique was developed for Hubble images. We leverage that a lot. It's otherwise referred to as subsampling or linear reconstruction techniques or co-adding. A lot of different names. But if you can see, here's a single image, and here is, I'm not sure how many images are stacked here, but you can kind of see how much the stars pop out. You get extra stars. You get even more precision in your pointing solution. And then also your target. There's Didymos, the Didymos Berry Center, being observed where it otherwise was not, and now there it is. And so it's kind of our basic process, and we re-register the stars and register our target, and that's our measurement. So yeah, here's some examples of an individual picture. Eventually it gets bright enough. You get close enough, it gets really bright. It starts to show up in the individual images. But again, these linear reconstruction techniques bring out a lot more spatial resolution, and so you generally get more precise measurements by still combining some of these images to increase the spatial resolution. It's pretty often that a lot of these imagers are pretty undersampled for people who know about that kind of stuff. The point spread function is sometimes smaller than a pixel, and so it can become pretty useful in terms of getting accurate registration to combine these images, increase the spatial resolution. So this is an example of kind of what we do. And here you can see we've observed it in a certain location based on our estimate of where it should be. It was predicted a little bit off. That's a pretty good predict. It looks like our trajectory is holding up, where we predicted things pretty well, although there's a slight offset always, but that's almost should be basically within the noise. Just another example of kind of how that looks on the image data. We're really caring about inspecting the each pixel essentially. Here's an example of what these measurements look like over time. So this is we're collecting all this data over the 30 days headed in, and these are the residuals. So the difference between where it was observed and where our best fit says it should be. If you think about that line fit, it's the offset between those points from our fit. And so it's pretty good. We see these things are nice and collapsed. The one sigma spread is around 1/10 of a pixel. As things get brighter, we get down to around 1 sigma of around 5/100ths of a pixel is typically what we really like to get to, although often 1/10 of a pixel is a pretty standard rule of thumb for how accurate you can observe things. And then, of course, in metric space, this is pixel space. In metric space, in actual kilometers, you see as we get close, we start to get the power of the measurement really starts to take effect. Where initially we're getting 1/10 of a pixel equals 10 kilometers. Now towards the end, we're just so close that we're measuring things to the meters, not to the meters, to the hundreds of meters essentially. Just some more pictures. The text doesn't show up very well, but this is about 1 month out. Here's what the measurement looked like, and this is basically how the signal evolves over time as things get brighter and brighter and brighter and brighter until eventually, you're really getting all the full PSF getting sampled out. And this is the very last image I think that we took before we handed things off to the terminal guidance. Other things, just kind of to talk about some other things that you really care about as an optical navigator. You really care about the pointing. Like when you're on the ground, you're gonna have very, very stable instruments. You're bolted onto the ground. The telescopes are controlled with extremely precise motors. Whereas in space, you're kind of just drifting around this whole time. A lot of spacecraft use reaction wheels, which are ways to really precisely control attitude. For the DART mission, it was a lower cost mission and it only relied on thrusters. So what you end up having is over the course of your imaging, you're bouncing around. You're telling the spacecraft point inside this box, and then it's going to try and stay in that box, but it's going to just bounce around the whole time. So you really, this kind of just smears your images, weakens the signal. It's something you really have to care about when doing optical navigation, is that intersection with a GNC. And so one thing we came across was during the first 17 days of approach, the spacecraft was bouncing around about 10 times more than it was supposed to. So we had really high smear. I mean, the stars were streaked across many, many pixels. And I kind of didn't really touch on this, but the Draco imager was a rolling shutter. So when you have this type of motion with a rolling shutter, you're really distorting your images. So this was something we hadn't really come across doing optical navigation before, and so it introduces a distortion of your star field and can introduce additional errors in your measurements. So we really had to care about this, and it was excellent working with the APL GNC team. I mean, amazing team there, and they diagnosed the problem, implemented a fix 13 days before impact, and you can see the difference. This is in the same one single imaging batch, the difference in amount of dead banding. And so this really, cleaned up our measurements and really improved our data, reduces the smear, reduces the distortion from the rolling shutter. It was a great thing, but it was a big decision to make, because in one instance, we've spent all this time modeling this spacecraft when it's under this sort of behavior. So we try and estimate that behavior, and it's thrusting this amount. So we know, okay, when we image, the spacecraft's going to thrust this much, and this is going to happen to the trajectory. And you get all that data. And so you can predict that, and you factor that into your models, and you predict that forward. So it was a bit of a decision, 13 days before impact, are we going to change the spacecraft's behavior? It's going to now enter this new type of behavior where we're going to have to immediately try and characterize it. In theory, it should just be good. There should just be less forces, less thrusters, cleaner spacecraft. It should just be good. But it's something you have to consider is the value of having it cleaner, but an unknown cleaner behavior versus a noisier behavior, but at least it's a behavior you've been able to somewhat characterize. But it was the right decision to clean it up. And then here is just an animation kind of showing. You can kind of see the star field move behind. So we're tracking Didymos over these 30 days as it's moving against the background star field, as we're tracking it as we come in to intercept it. And you can kind of see the star shift behind it. And then towards the very end, you start to straighten out the spacecraft's trajectories start to get more linear, and you start to line things up. The stars start to slow down, and it starts to get brighter and brighter and brighter and brighter. And then that's our last image. So it was pretty fun. Yeah, and that's most things for DART. Now I'll touch on optical navigation for the New Horizons Arakoth flyby. So this was how I got my start at JPL. I got to best internship you could ever possibly hope for, which is an internship that just lines up exactly with flyby operations to the Kuiper Belt. I mean, it was amazing. Overview, and this is also an APL managed mission. Funny enough, I've basically worked on APL missions more than JPL missions at this point. It was, its primary mission was to fly by Pluto in 2015, but then it had an extended mission that was approved to go out and do a flyby of a Kuiper Belt object. I know, very interestingly, the object that they were going to fly by wasn't even discovered pre-launch. It was discovered during cruise out to Pluto that there was a candidate could do a flyby of. And so here's kind of a depiction of the trajectory as a launch in 2006, flyby of Jupiter in 2007. And again, these Jupiter flybys are really they unlock the outer solar system. You really get your gravity assist from Jupiter, and you get to shoot way out there and do the flyby Pluto in 2015. 2015. But yeah, there were a lot of challenges with this mission. So the flyby was occurring at 43 AU from the sun. Again, a 12-hour round trip light time. So you basically take the brightness of the sun that we are now and divide that by 1/43 squared, and that's how much dimmer the light is out there. So everything's there's just very dim signal out there. Also limits your data rate. You're communicating at these large ranges. And then we also happen to be pointed towards the Milky Way during approach. And so here's an example OpNav image of what it looks like when you're trying to take these long exposures, because you have to take a long exposure because it's so dim. But then you're also just getting this insane background star field. It was kind of funny doing this mission and then going to do these missions, and I really was like, oh, I thought there were way more stars out there. But yeah, and so there were all these concerns, and if you can see the units on the image here is only a 256 by 256. So we had to, in order, because of the limited data rate, we had to bin the images. So and it also helps with your signal. You take your full 1024 by 1024 image, and then you bin the pixels before downlinking them. The pixels the pixel signal is combined to give improved SNR and also reduce the data of you could send 4 of these images per 1 of your original images. So that's a key thing to do when you're data limited. And then there were also that's exactly it. Here's an example of what these binned images look like versus unbinned. So 4x4 binning really takes away a lot of your spatial resolution. And so this is kind of one of the things that one of the challenges we had to tackle. Again, here's again the difference between doing co-adding. This is where I really got to implement a lot of the research, some of the techniques that Hubble would use, and all these various subsampling and co-adding linear reconstruction techniques to help us improve these measurements while working on the JPL shadow navigation team. And so this is what the co-add looks like in the original pixels, but of course by leveraging this subsampling, combining images, we could recover the lost resolution from the binning. And then, of course, you look at that. It's hard to say what is what. Thankfully, the team had taken a large data set of background images much earlier, before Arakoth was in this region and had any signal at all to show up. We had a set of background images that could be subtracted to expose the target. And so you can kind of basically see on the left, just doing the background subtraction, and here's how your target shows up, kind of blinking that a little bit. And so there's still a lot of signature, because again, you have, the signal shape of the stars, the PSFs. You don't have very precise, super precise pointing. So every image is distorted a little bit differently. So there definitely, I think, are more advanced techniques you could likely do to transform your PSF into the background field PSF and do improve background subtraction. And now as a not intern, I would like to look into that eventually. But at the time, this was plenty sufficient, is implementing these methods to do this background subtraction to observe our target. And here's another little animation, not nearly as much data, and also I'll note things in this outer solar system are moving a lot slower. They're on these great long trajectories. So whereas DART you could see it was moving really rapidly against the background star. Here you see, if you can see, it is in a different spot now. It has moved a little. It's moving a little bit more and more now. You can see it's kind of moved a couple, in unbinned pixels, it only moved a couple pixels. And as you get closer, you start to see more motion, and it started to shift a little bit. But whereas before, I'd shown Didymos had moved across many field of view. This by the end, the last image data had moved about a half a field of view, again around 0.15 degrees. So and then here's the ultimate result. Behold Arakoth. First Kuiper Belt object flown by. Very, I think, incredible thing is all these patches were made before we had flown by the target. These were the mission patches, and the science team nailed the shape of the target. It was almost, you could get conspiratorials. How did they know how exactly it would look? But this is, interestingly, another very powerful measurement in the navigation arsenal is stellar occultation data. I know that's something the amateur astronomy community contributes a lot often, is when you have some knowledge of some of these bodies and you have knowledge of when they're going to pass in front of a star, you can disperse a team across the Earth and all point their telescopes at this target as it passes in front of the star and measure the time that the star gets dimmed. And then you basically have this shadow being projected on the Earth. And with all these assets around the Earth, you can basically say like, oh, up, in northern Canada, the star only went dim for half a second. Oh, around the equator, it went dim for 3 seconds. We know, oh, it's narrow up here and wide down here. And so basically, that's a simple version. But that was done for Arakoth, and it basically that occultation data suggested that it was either a binary object or a contact binary, because you basically got to see some of the dimness and the wideness, and then it pinched in a little, and then it went out. So it's like, okay, this could be a contact binary, and they nailed it completely. Now I'll touch a little bit on Psyche. Now we're talking a future mission. I've only barely been involved in Psyche, so talking a little bit outside my depth here. But yeah, Psyche is a JPL mission launched in when was it? What's that number say? 2023. There we go. It launched in 2023 to go visit. The spacecraft is Psyche, and it's also going to the asteroid Psyche. This does cause problems to the navigators. It can be a bit of, yeah, you got to be careful. There's specific nomenclature for what exactly that's a nav accident waiting to happen. And so, but yeah, so it's the largest metal asteroid, diameter 200 kilometers. I stole this from a presentation from David Seal on the Psyche mission. The key hypothesis is Psyche potentially the exposed core of a larger, different body that was, exposed due to some high impact where the core had formed, and then it had its, rock blown off during some high intense event, or was it created by slow accretion of metal-rich material? But yeah, so this is an object of extreme interest, and it famously gets headlines of like, this asteroid is worth $10 trillion, because it is a very large, resource-rich metal asteroid. And so, the raw numbers are if you took market rate. If you took this asteroid and sold it at current market rate, you would be very, very rich. But I would not recommend trying to do that. But yeah, so the Psyche mission launched in 2023, uses 4 Hall effect thrusters for propulsion. Relevant thing, and demonstrated deep space optical communications, very successful. So right now it's coming up in May 2026 will be its Mars gravity assist. That's kind of the event that's coming up. The spacecraft is in flight right now, with expected arrival to Psyche in August of 2029. So a key distinction here is, in the past we were talking about largely point source registration, almost very one-to-one, comparable to ground astronomy, ground astrometry. That's what we care about, the astrometry of these images. But now we're talking about getting into orbit around a body, and I kind of touched on this before. There are crater matching methods, but basically now you can't just look at this and say, oh, here's the center of it. You're now up on this fully resolved body with all these features. So what's the best way to navigate around that? So yeah, the point source examples were DART and New Horizons, and now Psyche is an extended body. During approach, you'll image it and it'll be a point source, but you're also coming up on it so much slower that you don't have to take these longer range images to really get things. And each mission can have a bit of both, but it's there's this kind of key distinction between what these images look like. I mean, as you can tell, they're very, very different looking images. So early approaches really focused on craters. You would create a map of the craters, register the rims, and this is still done, especially for very large bodies where it's tough to create these huge, maybe shape models. Lunar missions, famously, if you call into some of the stuff that Intuitive Machines has done recently, they are leveraging crater rim optical navigation in their landing attempts, and that's still pretty common around the moon. But the current standard practice for small bodies is the use of stereophotoclinometry. This was a technique developed by Robert Gaskell when he was at JPL for, I believe, for the Dawn mission. Particularly, it was also tested in collaboration with a ESA mission, and yeah, it is this technique often referred to as SPC, and it's basically the approach of you collect all these images of your target. Instead of just saying, oh, these craters are our landmarks, what if anything can be a landmark? What if we pick a region on the asteroid and we have all these images at these different illumination conditions? Let's model that. We know reflectance laws. It's a very straightforward environment. Let's just model the albedo, the angles of the light, where we think the spacecraft is, put that all into one filter, and the heights, and you're also modeling the heights. You're basically trying to put all these things into one big estimator and then estimate the shape model, essentially, and the spacecraft. And so you basically can put all this together to create a global shape model of heights and albedos. And then when you have an image, you basically have your image. And here's some snippets from an image where here are all these regions. I'm looking at these in an image, and then I have my estimate of where the spacecraft is and my shape model. I can render that exact region and then cross-correlate them and match them across the body and get all these observations of the locations of all these landmarks across the region, and then observe all of these and track all of these as I'm maintaining my orbit around the body. And with that, have really precise relative navigation around this body. And here, just to the right, this is just some simulated data. Nowadays, I'm working on implementing this technique and setting up our tools to be applied to the MMX Martian Moon Explorer mission. So here's just some example fun simulated data I thought was cool to show of, again, here we have really good shape models already of Phobos. So that really is, very, very useful to leverage for this mission. So you can take that shape model, render it, simulate it, but also Phobos is orbiting Mars. So in some instances, you might have Mars in the background. And, here's kind of an example of, oh, here are all these landmarks where we wouldn't want to observe them because technically the lighting conditions at these exact points aren't ideal. So let's focus on the more well-lit ones. And these would be our measurements. And they're a nice, better, they're the right color, and these are the wrong color. But yeah, and that really covers the process of doing near asteroid extended body registration techniques. And this also can get applied to the moon or other really any non-atmospheric body. The atmosphere really introduces problems to this approach. You can't really, when all these models are changing due to a dynamic atmosphere, it becomes very difficult to properly create a model from imagery alone. And then kind of the final big section is autonomous optical navigation. So basically, we're talking about all these goals to fly these missions, and sometimes they just can't be achieved by the ground navigation team. I think DART is a perfect example. It would be nearly impossible in fact, for DART in particular, as a binary system, it would be impossible for a ground nav team to target and impact that asteroid. Although I do have a fun fact with DART is we actually did deliver the spacecraft so accurately that if the spacecraft had failed and not engaged its terminal guidance, it would have impacted the primary body, which is maybe not a good thing actually, because then you can't have a backup plan. Yeah, it would have been something. But otherwise, that's still a larger body. That was a 600-meter object, and we barely had our 3 sigma ellipse fitting within that target. Whereas the moon Dimorphos is 160 meters, and so that's we could not have had a full 3 sigma 99% confidence that we would hit that small moon because it's just so small. You have to take data so late that you just can't close the loop with the ground, and that's really those key things are to do full flyby tracking, to really track during a full flyby. You don't have enough knowledge to tell the spacecraft, oh, point here, point here, point here, point here. You will just miss the target because you don't really know. That's kind of a key thing with optical navigation, that I skipped over a little, is you don't know how far away things are very well. You know, you're looking at where it is, but you don't know how far away it is. So when you're flying by an asteroid, you can know very precisely where you're going to fly by, but you don't know exactly at what time because it's hard to measure the range. And so doing flyby tracking is tough because you really want to leverage some onboard capability to enable that. Impactors, then that's really taking the flying, where are you going to fly by, to the ultimate extreme where you kind of need to leverage onboard capabilities. And then also there just are very high dynamic environments where you just aren't, it's not really the right call to try and have a nav team design a burn every 3 hours. You know, there are certain regimes where the dynamics are so significant and sensitive that you want to have an onboard system that can close the loop a lot faster. Yeah, because really the full process of a ground nav team is you downlink your last measurement, you do OD, you design a new maneuver, and you uplink that to the spacecraft, and then put within that all the human processes of discussing how things go, how does this look, you know, reviews, everything. You really want to have a comfortable amount of time to do that. I think you can push that down to a handful of hours minimum, but that's very rarely done. Very critical things can sometimes involve that. I'm not sure what the shortest turnaround time is that's been demonstrated. But otherwise, yeah, you really often want around 24 hours. You know, you don't want to have this be super crunched. But what you can do is leverage autonomy, just doing all this stuff on board. And I just put a note that there is a lot of overlap with things that are discussed here in onboard optical navigation with, just autonomous robotics in general, with what, autonomous Mars rover planning, doing TRN is another way to describe this, terrain relative navigation. There's a lot of overlap with all these fields for doing precision landing. Landers are doing terrain relative navigation. The Mars 2020 had a terrain relative nav system to do improved landing and hazard recognition. So there's a lot of overlap with a lot of these fields. But yeah, so I'll really go back to Deep Space One, launched in 1998. So this has been it's been a technology for a long time. At this point, a lot of it is just engineering development to put these things on board. The technology itself exists. This was, the first demonstrated use of autonomous optical navigation using JPL's AutoNav system. So Deep Space One performed autonomous nav during cruise by imaging planets and large asteroids. So basically, as you're going through the solar system, you can kind of triangulate yourself based on these moons and the asteroids and kind of get a triangulation, not a super accurate one you often are in the hundreds of kilometers of uncertainty or even thousands by these long-range triangulation efforts. And then you can, basically Deep Space One would do this, and then it would look at its trajectory to update the electric propulsion plan to continue guiding to its target comet. And then during encounter, it would begin imaging the target as you're coming on approach. And that's where you're really close. You get these really powerful measurements again, and then it can track during flyby and refine the onboard estimate. So this was, launched in 1998. It was a very successful mission. The first flyby was a failure. There was issues with the image processing, getting fooled by a cosmic ray, and it had to. But luckily, there are multiple options to really work on this technology and develop it and demonstrate its capability. And here's some example flyby images of it. Collecting more distant images and then continuing to track the target as it got closer up until flyby. And here's kind of a graphic from the Deep Space One Autonomous Navigation Validation Report. And kind of since then, there's the Stardust mission also leveraging AutoNav. Again, I mentioned this before. Did multiple comet flybys along with a key capability distinction was the flyby of asteroid Anne Frank, which was detected fully autonomously. The flyby was occurring at such a high solar phase angle, which means the camera was pointed towards the sun. So when you're pointed towards the sun, you're seeing the backside of the asteroid. So it's very dim. This was a 140-degree solar phase angle. So it's the highest solar phase angle flyby that's ever occurred. And because it was so dim and poorly lit, it was not detected by the ground team. So they basically just saying, we're going to fly by this point in space. We think the asteroid's going to be there. we'll tell our onboard system to start looking for it at this point in time when we think it'll be bright enough to be found. And AutoNav was able to initialize, and at that point it was bright enough and distinct enough that it was able to lock onto it and perform a distant flyby. And then Deep Impact was the first impactor. And so this is kind of this spacecraft here. So it was a kind of flyby mothercraft with a large imager that deployed an impactor. And then that impactor initialized and turned on 2 hours from impact, and then leveraged 3 maneuvers to target Comet Tempel 1 for impact, while the main flyby craft imaged the impact as it flew by. And that's kind of what this example image is here of striking this comet. And then, more recently, DART, which has leveraged APL's SmartNav. And that used autonomous optical navigation to impact Dimorphos. And then a little bit recently as well is the OSIRIS-REx mission. This was an onboard system developed by Lockheed to do autonomous landmark registration in order to do the final sample collection guidance. Basically, they had to develop this. They realized they needed this capability while around the asteroid because the terrain was just so hazardous that the requirements of needing to precisely sample were so intense that in order to do this, you needed autonomous navigation capabilities. And so that leveraged autonomous landmark tracking to precisely arrive at its sample location. Lots of stuff kind of coming down the pipeline. There's the ESA's Hera mission, which is going back to Didymos and Dimorphos to kind of observe how does it look now after the impact. And then the JAXA's MMX mission, also a lot of sample return stuff often can require some sort of autonomy because you really are going down and having to potentially deal with hazards and very precisely sample and return safely. So that's often where autonomy gets brought up as a required thing. And then, it's also getting explored for lots of small sats. There's kind of 2 sides of autonomy. You need this capability in order to do the science. And then there's the other angle of, with autonomy, we can reduce operations costs. There's kind of the need to have versus nice to have because it reduced costs. So that's kind of getting explored more from the small sat angle side of things, is how can we do things cheaper by just not having to communicate with the DSN, especially as the DSN gets more and more burdened. And then there's future missions really it's as you pursue more and more ambitious science goals, more dynamic environments, getting into orbit around Saturn's moons, Jupiter's moons. Those are high dynamic environments, and doing more sample return, doing a lot of these ambitious mission goals are going to really require autonomy to be enabled. It will be a key enabling technology of the future for sure. But and I mean, that's, I guess, comes to my last slide. Just some great references of, there's a great book that was written called The Navigator's History of NASA's Deep Space Navigation. Some technical readings. There's Dr. Lincoln Wood at JPL has a great series. A lot of this stuff I referenced. A lot of the stuff here is referenced from there. On really, I mean, if you want a description of every single mission, interplanetary mission that's been flown and the nav story behind it, it's a great read. And then Dr. William Owen, who kind of was my mentor when I came to JPL as an intern, has a great paper on just optical navigation and its history and the fundamental mathematical models that are being used and are still largely used today. And that's it.
Test. This is the bad microphone. All right. Let's take some questions. We have some online. And a lot of them from somebody named anonymous attendee. Somebody wants to know, what is ephemerides?
Ephemerides is the orbits. It's a term to describe the orbit of a body in the solar system. Basically, it's often you refer to its ephemeris, which is yeah, can be exchanged with its orbit or its trajectory. Those are all the same.
All right. Another question from Mr. Anonymous. Why is CubeSat harder to navigate?
CubeSats are harder to navigate because they're lower cost systems. Again, for example, I mentioned reaction wheels. These are wheels that can store the momentum of a spacecraft and can spin the spacecraft around purely by spinning things up to exchange momentum. And there's no thrusting involved in those. And so there's no external forces. It doesn't change your spacecraft's trajectory to spin a reaction wheel. But those are expensive. Those are more expensive, complicated systems. So when you have to do all your attitude control with thrusters, you're always going to have a more noisy trajectory because you're trying to just spin the spacecraft, but there's always going to be uneven thrusts that you're not just spinning the spacecraft, you're also shifting it. So that adds up. And then there's CubeSats often just can have leaks. Systems, other things fail. There's just a lot more that can go wrong. I think over time, I'm sure that will improve, but nowadays, there have not been that many interplanetary CubeSats in which the challenges of navigation have really, in the way to make these things clean to fly, is still development.
A question about the image stacking. How far apart are the images taken from one another when you are doing the sequence of navigational images?
Those are taken, I think they were just taken 1 second apart.
Okay.
It's definitely something you have to keep in mind because as you can only stack so much because you'll start just stacking. If I had 1,000 images over an hour, by the time I'm stacking the last image, the asteroid has moved off of the first image. So that's kind of your fundamental limit to implementing that, is when the overlap starts to die. But for these environments, that was not a challenge over the stacking interval we were looking at.
What would you need to do to optically navigate to an object like Oumuamua, which has a weird shape unknown elsewhere?
That's perfect. So that was my master's thesis, was looking at doing nav to Oumuamua and Borisov and interstellar objects. So Oumuamua would definitely be very challenging because of that shape. So again, we're talking more about point source this whole time. So you wouldn't ever really be exposed to the shape and how it would be to navigate around a shape like that and what that gravity field and those effects would be. It would largely point source. So you would be dealing with large fluctuations in signal strength where that would maybe be something you'd be concerned about if you didn't think you could observe it when it's, you're looking along its long axis versus on the profile view. But otherwise, the real challenge with those is you're entering this rapid response architecture where you have to respond really quickly, and these things have only just been discovered, so their orbits are very unknown. And so those things all come together to create really as challenging of a navigation environment as possible, where you think of Anne Frank, where and also the speeds are so great. Then the speeds are so great, and therefore the distances are so great. And the distances are so great, therefore things are extra dim. So it becomes more challenging in basically every way. And so you really just have to kind of have you have to detect them early, refine their ephemeruses, launch to them, and then you have to have a likely autonomous navigation capability to target a precise flyby. And that could involve detecting it autonomously because it could be so dim. Especially the geometries of the orbits also lend themselves to high solar phase angles. So they're very, very challenging targets, but definitely hopefully something to do.
We'll take some questions from the audience now, Rebecca.
Yeah. Oh, hi. Yeah. Couple questions. One, said you couldn't detect the range, but I mean, couldn't they put like a radar on the satellite so that they can measure the range exactly?
So when you're in orbit around a body, and the distances are short, they often use LiDAR systems are used. There are like kind of range radar, laser rangefinder systems. But the problem really is it's really a distance thing. It really is. You're trying to collect these measurements so far out, and the relative speeds are so high that even a day out, you're hundreds of thousands of kilometers away. And so it becomes mainly it's a power thing. In order to send a strong enough signal out and then have it also bounce back at that range, so that distance times 2, it just takes so much power. And spacecraft are very often power limited, especially in deep space. You have these massive solar arrays. And so the amount of raw power needed to do that is largely prohibitive.
And just one other question. How do you know what the sky is going to look like somewhere up from somewhere else? Like, it's on that orbit, and you're measuring, the angle from the known thing.
Mm-hmm.
How do you know what the sky's going to look like out there?
So we're relying on the fact that basically, stars at these, we're looking at stars that are so distant that they are essentially at infinity. No matter where you are in the solar system, when you look at the star field, it will look the same no matter where you are in the solar system. Like maybe if we had Voyager take an image of the closest star to us, there might be some parallax there where things would start to shift. That almost sounds familiar that they've looked at that, and some instruments have looked at that. But otherwise, in the inner solar system, the sky looks the same no matter where you are.
The camera looking at the star patterns will give you basically a bearing line. Is that correct?
Yes. Yeah.
So then how do you get the ephemeris data from just one bearing line, or do you have multiple bearing lines?
We're collecting multiple images over time. So that definitely lends the strength of the measurement. That kind of gives you more complete measurement. You want more. But you also are piggybacking on all your ground observations. So you already have a fairly constrained orbit. Like if you think of the orbit as this big donut, this big tube of uncertainty, because we already have pretty good models of it. So as soon as you get this bearing line, it's like a slice or a pencil shot through this big donut. And now you've nailed down the orbit too. It's no longer just this giant donut. You know that it's somewhere along this line, and that can really collapse your uncertainty. So you're leveraging all these other constraints because have all these ground observations. If it's the first time you're detecting it, and that's your only measurement, you really don't know anything. Yeah.
Other questions?
For something like asteroid deflection, could you talk about the thinking around the angle of approach to that you would select to deflect the asteroid in a certain way?
Yeah. So the ideal situation for deflection is almost always directly along the velocity vector. Like if you could hit the asteroid exactly along its velocity vector to just perfectly either slow it down or speed it up, that produces it has the largest effect. Like let's say it was going to hit the Earth, that is your most sensitive direction generally to produce the largest shift in position for when it would have its Earth crossing. But that's very difficult because it's really hard to line things up like that, basically. So you would, in all, I think the process would have to be to look. You'd want to design those angles in totality. If you were to really do impactor deflection, you had to send multiple impactors. You're not really just designing each impactor individually. You want to look at the collective of like, okay, if this one can impact in this angle, when's the next one going to impact? Oh, the next one's going to impact, if we pick this orbit, it'll impact the exact opposite and cancel out what we did. Oh, we don't want to do that. So it is fairly complex because you are very constrained by orbital dynamics. So you can't just kind of fly around whichever way you want. You really have to look at the available transfers that you have and what the resulting geometries and what's the best collection of those. But if you had just one and you could put it anywhere, you'd want to put it directly along the direction of motion of the asteroid.
Thank you, Rebecca. Gosh, I have 21 questions. So some of them I'll just ask you afterwards.
Okay.
I'm going to try to hit the high points here. The first thing I want to make very clear to everyone is, according to what you're saying, the impact with Didymos, the last part of it was autonomous, was it not?
Yes.
Okay, because there's no way. Now I was looking at that chart you had there for okay. So the last image for Didymos, how long before impact was that roughly? A day?
The last ground image was 12. This is taken 12 hours before impact.
Okay.
But the last image that was used to update the trajectory to design a maneuver
Yeah.
was 2 days.
Okay.
So we took it. Our data cutoff is 2 days before. We
Yeah.
say, that's the last. Now all this data we have, use this, design a maneuver, and that maneuver was executed 1 day before impact.
Cool. Just amazing. Now, I was looking at that magnitude versus time chart that you put up there for the Didymos encounter, and I was trying to estimate it, but it looks to me like 12 hours before the encounter, the magnitude was 8th magnitude. Is that right? Something like that? There you go. That's it.
Yeah, I think so, something around that.
So
yeah.
this thing is really faint, even just a few hours before encounter.
Mhm.
So this is an amazing accomplishment being done by the telescope that's aboard the encounter. It's got a very narrow field of view. I think you said the
Yeah.
field of view was, it's like 30 arc minutes or something, maybe less than that.
Yeah, 0.3 degrees.
So 0.3 degrees, 0.3 of, yeah, about 20 arc minutes. So it's got a narrow field. It's got to make sure it's pointed the right way, and then it's looking for something that's really dim,
Yep.
and correctly identifying that it's going to the right thing.
Yeah, if you crunch the numbers to when the autonomous system is turned on,
Uh-huh.
I think that also helps with it a lot. Is the difference between how bright it is 12 hours out versus how bright it is. The autonomous system was initialized 4 hours out, and the past autonomous systems were often done around 2 hours. So you really do wait until by the time it gets to 4 hours, or that you're getting a factor of 9 times brighter. So it gets pretty meaningfully bright pretty quick once you get into that terminal autonomous phase.
And again, if it's using AI, it can say, hey, I should go for the thing whose brightness is increasing most rapidly.
I wouldn't necessarily say AI. I mean, I guess it is onboard intelligence, but yeah, the method is often I believe the main filtering method was a blobber, which basically you look at a signal and you look at how many pixels are connected to that signal. How large is it in pixels?
Uh-huh.
And we knew that I think that after a certain amount of time, when it was initialized, it would have to have been X amount of pixels, and so it would be bigger than any stars. And also the images, I think, were short enough that no stars were showing up. It was only, yeah.
Aren't you happy that you didn't have the Milky Way as a background?
Yeah, exactly.
Yeah.
Yeah, I wish I showed. There's a great. I mean, the whole 4 hours was live streamed, so you can watch the whole encounter in real time for 4 hours. You can watch every image come in 1 second. One image every second would come in, because the impact occurred so close to Earth. They could stream images. It's really incredible. And you see it as 1 second as it flies in at the very end.
A lot of us did. It was extremely exciting.
Yeah. I recommend.
Not that we're geeky or anything.
Yeah.
Okay. The question is, when will my wife take the microphone away from me? Okay, let's see here. You used several terms that were not, there she is. Oh God, no, you're not allowed to use the cane. Can I just ask one more question, or do you have other questions here? Okay, I can have one more. Okay, I'm going to ask more after. I hope he doesn't leave early. Okay, you used several, gosh, I've got so many things to ask. All right, you mentioned Cassini. You said Cassini was particularly precise. Can you compare it with another mission and just give us an idea roughly how much more precise Cassini was? Sorry.
Unfortunately, I didn't work Cassini, so I'm more so just regurgitating common nav discussion that I've heard from my peers and from my mentors who have talked about the past missions. Just the term Rolls Royce gets tossed out of to describe Cassini and the quality of spacecraft it was, and so it would be tough to put numbers behind it, but I'm sure I can find a way of it.
Okay. Cassini is very near and dear to my heart because I got to see it there at JPL before it was launched.
Oh,
And my wife is about to grab my microphone. Okay, here, but I want it back.
Any other questions? Any more questions? Thank you very much.
Okay, awesome. Great.